So this is our one and only one lecture in Chapter 7 on external flow. Here's the chapter. By the title of the chapter, you could tell. It's like, okay, I have flow that's external to a surface. It's outside the surface. Guess what the next chapter is? Internal flow. Flow inside of ducts or pipes. Okay, inside of heat exchangers. But this would be on the outside. Over a building, over a wall, over a fin, something where it's external. Okay, first part, 7.1. What's the title? What is that word? Empirical. And then we're going to spend a lot of time talking about flow over a flat plate. The flat plate's parallel to the flow. It's aligned to the flow. We'll review the Blasius solution, which is in, I think, almost all the fluid dynamics textbooks. It's pretty slick considering the difficulty of the problem, but probably over 100 years ago, Blasius worked it out analytically, and then he stayed analytical, but since computers have come about in the 1960s and so, now you take it so far analytically, and then you move to numerical solution of his very different ordinary differential equation, very abstract with similarity variables in that, to solve for the velocity profile in this flow over a flat plate, so the Blasius solution. And then we add the heat transfer, having a hot plate, isothermal, both for laminar and turbulent flow. Laminar flow, turbulent flow, local H, average H, local Nusselt number, average Nusselt number, local skin friction coefficient, average. There's so many equations your head starts to spin. But try and keep it straight. What am I looking for? Something to do with friction, something to do with heat transfer. Tau or H? Do I put it in this dimensionless form, skin friction coefficient or Nusselt number? Am I looking for an average or a local value? All I can say, there's a lot of equations in this chapter. Okay, then there are some correlations that are developed empirically. For, this is analytical / numerical, which is very neat, but then after a point, you just have empirical correlations based on experimental measurements. And whenever you get these, don't think that they're so accurate they can't be ever updated or modified or anything else, or somebody's measurements over here and somebody's measurements over there. They have to be in perfect agreement. They're typically not. There's a lot of uncertainty in these correlations. Plus or minus, I would say 25% is not unusual, which is a little frightening to students. Like, man, I've been given answers on my calculator and on my exams to 7 significant digits. It doesn't make any sense to make calculations of convection heat transfer with empirical correlations to anything near 7 significant digits. Okay. Then there's a nice section. I think you should really read that section. It's how do you solve convection problems? Because there's so many steps and it seems like you can get so easily confused. Well, there you go. Then we'll cover cylinders in cross flow, spheres in cross flow, or any flow around a sphere. And then the rest of the chapter, even though it's very important about jets and arrays of tubes and stuff like that, we're just going to skip it. Let's jump into it. Last chapter was so important. You really cannot build and understand this chapter without understanding the precursor chapter, chapter 6, where we talked about the boundary layers, continuity equation, momentum equation, energy equation. We're going to start there for the flow over the flat plate again. Shear stress, friction coefficient, convection coefficient, Nusselt number. So we go from tau and H to C sub F and Nusselt. Hey, what are the SI units on the shear stress? Newtons per meter squared. Hey, what are the SI units of the friction coefficient? Dimensionless. Nothing. What are the SI units for the local convection coefficient, H? Watts per meter squared Kelvin. Excellent. Nusselt. Dimensionless. All right. And then the last of the chapter, we brought out this equation. What is that equation? It's an analogy between what? momentum transfer and heat transfer. This is associated with momentum transfer. This is associated with heat transfer. All right, so we have the heat transfer associated with the momentum transfer through these, additional Reynolds Prandtl to the 1/3. This is a modified Reynolds analogy or Chilton-Colburn analogy. There's a range of Prandtl number which they verified and agree, but don't take it outside of these ranges. That's one thing you'll see on a lot of correlations. They'll have ranges of, the Reynolds numbers between here and here. Don't go outside. Don't apply this correlation to a Reynolds number above this limit or below this limit. Same thing here. Don't use this equation if you have a fluid with a Prandtl number of 1,000. Don't do it. So watch your limitations. But we're going to use this equation once or twice in this chapter. And then we'll also see where it's not applicable in this chapter. Empirical. An empirical correlation is a correlation that has been either promulgated by the king, promulgated by the queen, developed in the English-British system of units, inferred by experimental measurements, or derived theoretically by analytical methods. What does this empirical correlation mean? Yeah, let's show the results. Well, nobody thinks it's the king or queen promulgating it, dictating what it's going to be. It's really not associated with any system of units. Empirical sounds like it. Sometimes you'll see the empirical with like an I, empirical system of units. That's old terminology in my opinion. Anyway, it's based on experimental measurements. That's the key. That's the key. It's not derived analytically or theoretically. It's just based on a lot of measurements, and then they do some curve fitting of those measurements. They often take the physical measurements and put them into dimensionless groups or parameters such that you'll have some abstract Nusselt number as a function of the Reynolds number, and they'll have a sequence of data points, and then they fit a line to it, maybe on a log-log plot to get the exponent. Well, we need to jump into this. The Blasius velocity boundary layer solution. This is the name of an individual over 100 years ago. Did this work? Who's heard of Blasius out of fluid mechanics? Yeah, a couple of you. Good. Yeah. So this is just a review. What did they solve? Well, you have the flow approaching U infinity everywhere before it hits a knife edge flat plate. And it's aligned with the x-axis. And you're going to be able to solve for what we really want to solve for is the u as a function of x and y right in that region, and v as a function of x and y in that region above the plate. So it goes from the tip off to infinity, or you could put L, the ending point of the plate. The plate has to end somewhere. Or y goes above the plate from 0 out to infinity. That's the range. You're interested in the velocity u and v, the x component and the y component of the velocity. And what you're really, really, really interested in is what's happening at the surface. So at every location we sketch that velocity boundary layer profile, right? And we're interested in the slope right here. What is the rate of change of the u component with respect to y at the surface? Why? Because we use somebody's law of viscosity, sometimes you just call it law of viscosity or Newton's law of viscosity, to determine what's happening at the shear stress. Isn't the shear stress tau? What is the equation for that? The shear stress at the surface is mu du dy at y equal to 0. All right, is the shear stress a function of the location x as I move down the plate? Yeah, because the slope, du dy, is changing. So how do we solve then for this shear stress? Well, you start with these two PDEs, partial differential equations. What does the first one represent? Continuity, conservation of mass. What does the second one represent? Momentum in the x direction. I didn't even write the y direction. Also, is there a a pressure gradient, a dP dx in this equation. Is it written? No, it's not. So out here, far away, we have P infinity. P infinity. And how does the pressure change, P infinity change, as I move increasing x far above the plate? Does the pressure change as I'm moving in the direction of flow far above the plate? There's no reason that the pressure changes far above the plate, even in the direction of flow. Now, what you're thinking is, you're thinking of pipe flow, internal flow, and you're thinking of the pressure in the middle of the pipe, and the pressure is going to drop as you're going down the pipe. But this is, external flow, and far above the plate, the pressure is not changing in the x direction or in the y direction. Somebody says, well, what about close to the plate? Does the pressure there change as you move along? Nope, does not. So basically the pressure is not a function of x nor a function of y, and that really is, I skipped that step. I'm just saying it in words, but it comes from the y momentum equation. All right, so we don't have a pressure gradient pushing it. What does this term in the momentum equation represent? The viscous term, the diffusion of momentum due to viscosity of the fluid. All right, what's this one? Advection of momentum. All right, let's continue on. What did I write all in here? What's all this? It's like I have some PDEs. Hey, I forgot. What does that acronym stand for? PDE. Partial differential equation. I have two of them. And I'm trying to solve for U and V everywhere in my domain of interest. This is the domain of interest. And I need a lot of boundary conditions. And that's what's in this box right here. Aren't they all my boundary conditions? Yeah. And so what does this boundary condition right here represent? U at any x at y equal to 0 is equal to 0. What does that represent? No slip at the plate, at the surface of the plate. Y equals 0 is the surface of the plate. So any x along the surface of the plate, you have to have no slip. And likewise, there's no penetration. It's not downflow going into the plate. So the V component is 0 at the plate as well. And then far away, you have just the free stream, and then you have no up or down flow far away. Y is off to infinity. That's far above the plate. Okay. What is this one? This is my initial velocity profile at the leading edge. At x equal to 0, any y, it's just U infinity coming in. Yeah, there's a singularity at the tip. Don't worry about it. Well, you ready to solve those PDEs? All right, so how did he do it? Well, he went back to a stream function. What? Stream function? Yeah. So you look for U as a if you could find the stream function such that you differentiated the stream function with respect to y, it would give you U. Likewise, if you could find a perfect stream function, differentiate it with respect to x, put a negative in front of it, that would give you V. That's basically the purpose or the looking for the stream function. It satisfies immediately the continuity equation, so this one's like done. Stream function, if you could find it, you can check it. It satisfies the continuity equation. But now we look at the momentum equation. It's like we knocked out one of the differential equations. We're left with one of them, the x momentum equation. We look for a similarity variable. This is the one that after, I'm sure, a few iterations came to light, hey, this is the one that works. So we have y times the square root of U infinity over nu x. What does that look like? Well, it looks like a Reynolds number in there, but let's not play with that right now. And then what we're interested in is a similarity solution, the function of eta, which you have the stream function divided by U infinity square root nu x over U infinity. Okay, so using these you can convert the remaining PDE into an ODE. What? That's the trick in math. You know how to solve a simpler problem, so you make the more complex problem look like the simpler problem, then you solve it like you know how to solve the simpler problem. Anybody remember Laplace transforms? I'm trying to forget it as fast as possible too, yeah. It was pretty torturous, but what was the trick in Laplace transform? You do this transform of an ODE to turn it into an algebraic system of equation, then solve the algebra for S's, and then transform back. And so the two transforms, usually you look for tables, how to do the transform. And then, so now it's like, hey, I took my differential equation, that problem, solve it as an algebraic problem. Okay, same thing here. We want to get an ODE. So there's a few steps in calculus. Aren't you so glad you took so many calculus classes where you transform u and you make it df d eta. That's what it boils down to. The derivative of u with respect to x, it turns into what I show you right there, negative u infinity over 2x times eta times the second derivative of f with respect to eta. Then you do all those terms. There's a lot of W-O-R-K. Don't you like four-letter words? A lot of work. And then this is the bottom line. Did I show you all the details? No, the book actually does a pretty good job. Can you see that this is an ODE? What is the highest order of derivative in this ordinary differential equation? Third. So we have a third derivative. And so now it's like so abstract, but this is what Blasius worked out, and it works. You're looking to solve for f as a function of eta. You take some of your boundary conditions, you transform them, you get f at 0 is 0, the derivative of f at 0 is 0, and the derivative of f at eta goes to infinity is equal to 1. I have 1, 2, 3 boundary conditions. Third order, it's all math. Easy from this point, isn't it? Just at this point, Blasius he was way before computers, and he did it all analytically. But now everybody just says, you know what I'm going to do is I'm going to solve this numerically. So in the textbook, they have this table. And what they have put in here is a function of eta. They remind you of the definition of eta. They put in f, the derivative of f with respect to eta, which, hey, can be interpreted as, they show you in the header. And then I am covering this up. Let me try and uncover it a little bit. The second derivative of f with respect to eta. And this is typically done numerically, and they solve that ODE for a range of eta. It goes all the way out. You can see here it stops, but you don't have to stop at 6.8. You can go on and on and on. But what's really interesting, or what's needed, is a few of these data points at eta equal to 0, especially the second derivative. And then if you come out here on the first derivative, where u over u infinity, we like to talk about the 99%. What was 99%? U over u infinity? That would mean that u is equal to 0.99 of u infinity. Does that equation look familiar? That's the extent or thickness of the boundary layer. So when you come down here to 0.99, you come across and you find that that's eta of 5. I know there's probably a few more digits on that, but close enough to 5. So the whole table boils down to 0.332 and 5. All right, so from the numeric solution, u over u infinity is the derivative of eta f with respect to eta. You're very much interested when it's 0.99. That's the extent of the boundary layer. You find that eta is equal to 5. Hence, you have the delta, which is the thickness of the boundary layer. That I substituted in the definition of eta, which y is. Y equal to delta at that point. The square root, blah, blah, blah. You rearrange, and what do you get? Underlined in red, you say the boundary layer thickness is 5x times 1 over the square root of the Reynolds number. That's in the fluid mechanics book, repeated here. Now we're interested in with the shear stress, very much interested in that derivative of u with respect to y at the surface. We do the math and we find that we really need the second derivative of f with respect to eta at the surface at eta equal to 0. That comes in numerically to be 0.332. So you substitute it right there. You can leave it in terms of tau, or you can introduce c sub f, the skin friction coefficient, and underlined in red is the bottom line with a few algebraic manipulations. 0.664 over Reynolds to the square root, or square root of Reynolds number. Now, sometimes it'll be written this way or that way, and you'll look at it and say, hey, they're missing a factor of 2. But what did they do here? We like to often put c sub f over 2, and then it becomes back to 0.332 over the square root of Reynolds number. I hope you find this helpful. I know this is too much to digest. You really need to go through it yourself. All right. Now, you can use the modified Reynolds analogy because we just worked out what c sub f over 2 is, isn't it? Didn't we just work it out that it's 0.332 over the square root of Reynolds number? You stick it in, and now you have an equation for the Nusselt number, 0.332 Reynolds to the half, Prandtl to the 1/3. That's your expected result, and it agrees with the more tedious, where you come in and introduce the energy equation. What's this equation? The energy equation. And you have to introduce some abstract dimensionless temperature ratio, T asterisk, that's what the book uses. And you transform with a little WORK, the energy equation, into another equation. This equation requires you to already have solved the Blasius for the u's and the v's for the velocity profile. And what do you get? Can you just look at this equation and tell me what it looks like? An ODE. It's an ordinary differential equation. Now I can solve using this Blasius approach for the temperature distribution. What are my boundary conditions given? Am I going to solve it analytically? Well, probably many years ago they did. But today we would solve it numerically. And if we're interested in H, the convection coefficient, we need that temperature gradient at the surface going into the fluid. And solved numerically, it comes in at 0.332 Prandtl to the 1/3. You do the substitution, you get the same result, although in the analytic derivation there's a restriction on the Prandtl number that's more clear. So, kind of like you could have not even transformed to get a new ODE and then solved it numerically. You could have just stayed with the modified Reynolds analogy, same result, but there you go. Let me ask you this. What does this NU stand for right there? What is that? Nusselt number. What does the little x subscript indicate? Local Nusselt number. How about if somebody said H with a subscript x? What does that mean? Local convection coefficient. These correlations are for the local values. So let me insert another page. Insert, new page. So if I have H as a function of x and somebody plots it like that, what they're really giving you is H of x, the local value. At this x, I get that H. All right. Somebody says, I want to go from 0 to L, and x is going out this way. And I want you to give me H bar. H bar. How would you do that? H bar is 1 over L, integral from 0 to L of H of x dx. True or false? Didn't we do that? Yeah, we did that. Likewise, you can do the same with the Nusselt number, the average Nusselt number, 1 over L, the integral from 0 to L of the local Nusselt number dx. So I don't make a big deal of it because there's so many correlations that you can get confused. But just think of it. If I've shown you an equation for a local, there's probably an equation for an average. Now, you have flow over a flat plate. You studied this before just from fluid mechanics. We just derived using Blasius about this laminar condition. We've even gotten how thick the boundary layer is. Well, with a little bit of work, you could find the thickness of that thermal boundary layer, the laminar thermal boundary layer. What did they put on the subscript on this delta? Isn't delta the thickness of the boundary layer? Without a symbol, it's for the momentum or velocity boundary layer. If you put a little t down here, it's for the t stands for thermal. And it's the velocity boundary layer thickness times a Prandtl to the 1/3. Pretty simple result. All right. You can almost see that if I went back in the pages and showed you how it falls out of that Blasius solution for the energy equation. Okay. But here, what happens here? Turbulent. Do you think you have a nice analytic solution for turbulent flow compared to laminar flow? No. What are you going to rely on? EMPRICAL. What's that? Empirical measurements. And so they do a lot of measurements and they come up with, hey, this is what works. We see that the boundary layer thickness, when it's turbulent, is about 0.37x Reynolds to the -1/5. Now also for heat transfer, well, when it's heat transfer, it's well mixed. And when it's well mixed, the velocity profile, the thermal profile, they're about the same thickness. So there you go. The thermal boundary layer thickness in a turbulent region is the velocity boundary layer thickness in the turbulent region. Boy, I tell you, there's a lot of correlations, isn't there? So we derived this one from the Blasius. What is it for? The friction coefficient. And also the Nusselt number, local Nusselt number. How about for turbulent? Now, I'm glad a lot of people worked out there before us, made a lot of measurements, and there it is. And what did they do here? What did they use to go into the turbulent region? Basically, they took the modified Reynolds analogy and applied it. Okay, so how did you, this is the modified Reynolds analogy. You just take the 1/2 of CF, the skin friction coefficient, substitute, simplify, same coefficient. You get a change in the Reynolds number from a -1/5 to a Reynolds number of 4/5, and the Prandtl number of 1/3 goes along. Make sense? I'm going to try and summarize all this, but it'll give you a headache. Laminar in the top half, turbulent in the bottom half. Boundary layer thickness, skin friction coefficient, local, average. And for heat transfer, thermal boundary layer thickness, the local Nusselt number, the average Nusselt number. Here I've written it average from 0 to L. You could write 0 to X, but then it's so confusing to students. For turbulent, notice that they give you the range of turbulent. What is the critical Reynolds number for flow over a flat plate? 500,000, 500,000, exactly. How many students will put down 2,300 for the critical Reynolds number for flow over a flat plate? What are they thinking of when they put down 2,300 for the critical Reynolds number? Pipe flow, pipe flow. You've just 500,000 and 2,300. Some people round off to 2,100 to 2,000. I'm not going to argue about that. It's 2,300, easy to remember. For pipe flow, 500,000 or 500,000 for flow over a flat plate. Okay, so they're saying don't take it out too high. I don't know why, but the experimental measurements, they didn't go to 10 to the 10th in curve fit. I'm sure somebody out there has done it. Just do a search. But in our textbook, they do put limitations on the range for the Reynolds number for these turbulent correlations. And there it is. Thickness, skin friction coefficient, thickness, Nusselt number. And I guess I could have written the average, but I didn't. You just do the averaging, same equation. So here I'm guessing they'll have correlations, and they'll say, look, we're going to do this. We're going to have an average over when it's only laminar. Great. You know what? They'll also have a set of correlations where essentially they'll just do an average over where it's turbulent. That's great. But then you say, don't we have the leading edge? Doesn't it start laminar always and then transition to turbulent? Couldn't I do a average both for laminar beginning and turbulent over? Yes, you can. And guess what? Somebody else has already done it, and it's in the book. So read your limitations or application of those correlations, because there'll be an average where you have some laminar, some turbulent. Now what happens is sometimes you'll find that the length at which it was laminar is so small that the length over which the plate is turbulent is so large that they just neglect that first little section. Hopefully some of this makes sense to you. Let's move on. Okay, so whenever you flow over a flat plate, a lot of correlations, a lot of them come from the Blasius velocity solution. When you get to the empirical correlations, especially for turbulent flow, don't think that they're super accurate. They're plus or minus 25% easy. Now, let's move on. This is a great section. Read this section. It basically, especially when you're brand new, you're trying to learn how to solve convection heat transfer problems, do this. Identify what geometry do you have. Do you have flow over a flat plate? Do you have flow over a cylinder? Do you have flow inside of a pipe? Do you have flow inside of a duct? What do you have? Then look for the correlation, because it does no good to use a correlation for flow over the cylinder when you have flow inside of a pipe. And yes, there's been many exams where students have used the wrong correlation. Okay, next one. Evaluate your fluid properties. Are fluid properties temperature dependent? Yeah, look at air properties, water properties, things like that. Well, then what temperature do I use, Professor? Well, most correlations use a film temperature. Does the film temperature look reasonable to you? What is it? It's the average of the surface and the fluid far away, free stream. That makes sense to me. So no problem. Just sometimes you don't know either the surface temperature or this mean temperature or free stream temperature. Hence, if you don't know it, you have to guess it, get some fluid properties, solve the problem, check to see how close your guess was, and maybe iterate. That can be confusing. All right. Flow regime. Is it laminar or turbulent? Usually that's a big dividing line. If it's laminar, go to these set of correlations. If it's turbulent, go here. Identify what do you need. Do you need a local H or a local tau, or do you need the average H or average Nusselt number, average something? Okay, often you find your correlation and they don't have, sometimes they can be very clumsy and long, but during an exam, time-limited exam in a class like this, we're not going to give you the correlation that needs to be coded into a computer program that's a little more accurate. Often we're going to expect you to use the simple form of the correlation, which is often a constant Reynolds to a power, Prandtl to a power. It really does boil down to plug and chug often, which I don't like. I like to have you think about what you're doing and know why you're doing it. But some students have passed this class purely on plug and chug. All right. Often you have to get the Nusselt number and unravel it to get the H, if that's what you're looking for. How do you unravel it? Just look at the definition, undo it. And then use the H maybe to predict the area that's needed or the rate of heat transfer or something. Hey, does this equation look familiar? Sure. It's our law of cooling. And iterate. Why would you iterate if needed? Often we don't know what temperature to get the fluid properties. Or sometimes we may have to guess that I think it's going to be turbulent. And then you find out, oh no, if I check the Reynolds number, it makes it look like it's laminar. Well, I need to iterate and go back and get a different correlation. So, but iteration by properties or iteration by correlation if you thought one was laminar or turbulent. Flow over a cylinder in crossflow. Again, one of the themes, if you really, heat transfer is easy. It's the fluid mechanics behind it that's hard. So does this this illustration look familiar? I know I grabbed it off a NASA website. It may not be one you saw. Maybe it's not the one in the textbook. Do you remember a similar illustration? So you have the fluid flow coming at a cylinder in crossflow. And what's this first case, second case, third case, fourth case, fifth case? What's changing as you go from 1 to 5? What's changing as you go from 1 to 5? The speed of the approaching fluid often is the simplest way to think about it. Because what happens if the speed of the approaching fluid goes up, up, up? You have a higher Reynolds number for that flow. The Reynolds number for flow over a tube is based on D. What is D? The diameter of the tube or the cylinder. So is it rho V D divided by mu? Is that it? And what again is this big V? That's our fluid approach velocity. And in cases 1 to 5, it's going up. Hence, that's why the Reynolds number is higher for case 5 than case 4, etc. Okay. You can even see it down here. They say, hey, turbulent. Okay. Anyway. So what about what are they showing you by these lines? Let me see. This line that goes like this. What are they showing? What is that line? It's as if I dropped a little pack of fluid, colored dye fluid, and I traced it. It would just go like that. That's the flow line, the streamline, streak line. Now, when it's steady state, and these are steady state, then all those terms boil down to the same thing. It's when it's transient that fluid mechanics, the difference between a streak line or streamline and what does it show about the fluid packet that's just a little above the center line? What does it do when it gets close? It just goes around, and that's it. And they have this one case right in the middle, like what? It's kind of hits and splits, joins and goes back. Okay, what happens here is the velocity goes up. Well, what do you get in the backside? Isn't this the backside in here? What's happening? You're getting some recirculation. So the fluid stayed pretty well attached and then got back together on the backside of the case 1, but on the case 2, no. It like leaves the surface right here and then gets back into where it needs to be. But in here, you have fluid circulating. Somebody says for this top one right here, does it circulate in the clockwise or does it circulate in the counterclockwise? A or B, clicker question. To answer that question, I would go and focus on this region right in there, where you have the fluid line on the top definitely going from left to right, and the fluid that's right below it, that's in that recirculating region, really can't be doing the opposite. It makes more sense that it's being dragged in the same direction. So it makes more sense that A is correct, because on the top outside it's going from left to right. So the correct answer is A. A. Okay. Now, as you increase, what happens here? What are you getting? Instead of a steady recirculation region on the backside, it's unsteady, and then they'll shed little vortices. And that shedding makes this tail wag, and a second later it'll be like this. And another second later it'll be like that, etc. It's not steady, it's oscillating. Then if you increase the speed, you get the separation up in here, and What do they say between 4 and 5? It's like separated, I get it. But they say laminar versus turbulent separated. What are they talking about? What are they talking about? What's the difference between 4 and 5? Oh, 5 is a little faster. But then they throw this term turbulent in. Turbulent separated versus 4 laminar separated? Well, what happens is I need to almost go to another plot. As you come around here, you have to understand what the fluid's doing on the first half. Let's just focus on the top, the first half of going around the cylinder. Think about what the velocity is doing. Let's pick a streamline, this blue line right here. What's the velocity doing as I'm going from point A to point B? What's the speed doing? Going up, going down, staying the same? What is it doing? It's going up. It's speeding up, isn't it? All right. Okay, where is the pressure lower? Oh, man. Is the pressure at A the same as the pressure at B? Or is it greater or is it less? Should I ask a clicker question on this? Why not? Answer A, B, or C. So is the pressure at A, the fluid pressure at A, compared to the pressure at B, where's A and B? Before the cylinder and then at the top of the cylinder. Okay. Is the pressure at A greater? Answer A. If the pressure at A is the same, answer B. And if pressure at A is less than the pressure at B, answer C. Okay, we're going to stop. Let me do this. Anybody heard of an equation, let's say, that I can then go and say something about the velocity and the pressure at this point compared to the velocity and pressure at that point, velocity and pressure at that point, velocity, pressure at that point, velocity, pressure at that point, along a streamline. I can't go off the streamline, but staying on a streamline, I can write one equation that says something is constant, something that relates the velocity and the pressure is constant along that streamline. For a limited number of conditions, it has to be incompressible, inviscid, steady state, you know. Bernoulli's equation. Can you recall Bernoulli's equation from memory? Pressure plus 1/2 rho. What is rho? Mass density of the fluid, and then V squared. Now you could put GZ in that and all that, but let's just leave that out. Let's neglect elevation, right? Is equal to, what is C? A constant. So if my speed goes up, what does the pressure do? Goes down. If my speed of the fluid goes up, and it needs to be a constant, the sum of these two terms, then the pressure has to go down. I'm going to re-ask the same question, this question right here. Focus on the pressure at A and the pressure at B. Answer A, B, or C. If you already had it right, great. Get 2 points correct on it. Otherwise, rethink it and re-answer. Let's go back. What did we say about the velocity at B? Isn't it greater than the velocity? Didn't it speed up? It sped up. So the pressure went, the pressure at B is not greater, it's less than the pressure at A. This is correct. So we have 71% of the classes correct. Do you understand? Hopefully if you're in the 30%, you understand why. Let's go back and take a look. Well, I was able to nudge you a little bit, but as a class, not that much, from about, 50-some% to 70%. All right. If you don't understand that concept, it is not going to help much on the next concept, because what's happening coming back over here, it's like the pressure's high, and it's going down, down, down. It's pushing the flow. It's what they call a favorable pressure gradient. If I have fluid, it's high pressure, and it's flowing in a direction of low pressure, that all makes sense. But can you turn it around? Can you ever have fluid flow from low pressure into high pressure? Can you ever have that case? Clicker question. Yes, you can. Answer A. Or no, you can never get fluid flow. Answer B. Can you have fluid flow in the direction where it's flowing from low pressure into high pressure? Answer A, yes. Or answer B, no. Let's look at the results. So, you can have pressure flow that way. Take a look at Bernoulli's equation. Maybe the velocity decides to go down. If the velocity goes down and it's constant over here, what does the pressure have to do? It has to go up. Professor, this doesn't make sense. Go back to fluids. Was there anything that was shaped like this and spelled N-O-Z-Z-L-E? What's that called? Nozzle. What about anything like this, which is D-I-F-F-U-S-E-R? Diffuser. The fluid goes in this direction. Here, let's get rid of that. This direction there. Now, nozzles, you love, you understand. I find the students, it's very intuitive to understand and work with a nozzle. Why? What's pushing the flow through the nozzle? It's high pressure over here, low pressure over there. It's low speed, high speed. Look at Bernoulli's equation. But a Bernoulli's equation works in the diffuser as well. What? Look it. It's high speed here, low speed there. Isn't that it for a diffuser? What's the pressure doing? Recovering. Now, you got to be careful when you build a diffuser. A nozzle, you can make it pretty steep in closing that cross-sectional area. If you have a diffuser, you better take your time. Otherwise, what's going to happen out here, you're going to get separation because fluid flow doesn't like to go that way. It's an adverse pressure gradient. On a flow in a cylinder, cross flow, guess what they call all of this region? Adverse pressure gradient. Fluid doesn't like the flow slowing down and going into a zone of higher pressure. It wants to do what it would do on the walls of a diffuser, separate. Where will it separate? It'll separate on this backside and start this recirculation like that. First, understand this slow, low Reynolds number flow. It's called creeping flow. It's also called Stokes flow in honor of Stokes, who studied this. Yes, it's very applicable. A lot of things, slow flow, are meaningful in science and engineering. And then you got to move away from slow flow. You got to move to faster flow. This whole adverse pressure gradient is a difficult, challenging concept. Guess why fluid mechanics is hard? Then, if you master what's happening to all the pressures, that's great. And then what you do is you find that you have this adverse pressure gradient region that you're flowing into. The flow near the surface has the lowest velocity. Because it has the lowest velocity, it's easy to sort of push back such that you get a stagnation point and that you even get flow reversal in the velocity profile coming out. Hence you get this wake region or vortices or this recirculation region. And then it can be oscillatory in shedding the vortices or the recirculation region, or it can be at higher flow, it can be very turbulent back there in this wake region. And so in this wake region, you get not good. I mean, you don't use Bernoulli's equation into that wake region. You violated one of the requirements of Bernoulli. What was the one? Along a streamline, inviscid. So there's some limitations to Bernoulli's equation. But you don't get perfect pressure recovery. You start to get a pressure over here that's low compared to the stagnation pressure, which is high. When you have Stokes flow, guess what the pressure at B is? The pressure at B compared to the pressure at D. Full pressure recovery. They're the same. But now you start to get the pressure. So when you look at the net force, pushing the net force, I'm trying to draw a force here, F, the net drag force, it's the sum of two components. It's the viscous, due to the viscosity, especially on the front half, and then it's the pressure, or form drag, all fluid mechanics, right? And that form drag dominates at high Reynolds number. And the viscous only dominates at Stokes flow or creeping flow. Okay. Well, this whole separation point concept, it's quantified by this angle of separation theta. In this textbook, they use theta. And so it could be where it's up in this region where it separates, or where here it looks like it's separating a little bit above past 90 degrees. But if you go to really high flow rate, the size of the wake reduces. That's a tough concept. That means the angle theta increases. And what happens is the form drag, that component, the pressure difference between the front side and the back side, because now the back side has a smaller wake region, that form drag is lower. Why does the angle, when I increase the velocity, why does the angle increase, this angle of separation change and increase? Well, we go all the way back to that NASA illustration right here, and it hinges on this word right in the beginning, laminar versus turbulent. What's laminar in case 4 and what's turbulent in case 5? Not the wake. The wake is turbulent in both cases. It's right before the separation. Before the separation, this region of the flow is laminar. Then you get the separation. If it's turbulent before, let's say it turns turbulent right in here, then this whole section's turbulent, and then it delays separation. You get a smaller wake.
Is there like an angle at which you go from laminar to turbulent?
Yep, that theta, that separation angle.
Is there like a specific, like a 90 degrees, 90 degrees?
So this illustration, I think all of you have seen in your fluids book. What's on the, I'm going to answer that question with this illustration, but let's build it up. What's on the y-axis? Drag coefficient. Okay, C sub D. Can you recall what that is? The force, net total drag force divided by 1/2 rho V squared. But that's a pressure I have to multiply by an area. It's the projected area of the, or shadow area of that cross-sectional cylinder. Okay. So that's the drag coefficient. What's on the x-axis? The Reynolds number. And then both of these are on log-log plots, aren't they? So they cover a lot of territory. At low Reynolds number down in here, what type of flow do we anticipate over that cylinder? Or even here they have a sphere and cylinder, so they doubled up the data on this one plot. But let's just focus on the cylinder and cross flow. What is this whole thing in here? Stokes flow, low Reynolds number, no separation. All right, no separation. They even emphasize that, so pointing to this region, no separation. And then there's some point they have this transition, and then they have the C sub D is now changing. It's pretty flat. I would say that, I know it's not perfectly flat, but in a pretty good range of this, it's pretty flat. And what do they say right up here? They're giving you the angle of separation. It's happening a little before 90 degrees. It's happening a little bit before. No, that's not perfect. It's not the same. I'm sure somebody's done a study and they found it, oh, it's 74 degrees here or 95 degrees here, etc. But, roughly. But then out in here, they really increased the flow, and there's this dramatic drop. What? There's a dramatic drop in the drag coefficient, meaning there's a dramatic drop in F, the total drag force, because 1/2 rho V squared is only going up. The V is still going up at higher Reynolds number. So to really get a drop in this drag coefficient, you had to have a drop in the drag force on my cylinder. And this is very interesting. And what happened right here? What are they saying? That separation angle went past 90 degrees. It went to 140. Smaller wake. And so what happened is you have the pressure in the wake region is still low, but it affects a smaller section of the backside of that cylinder. Hence, net total force, drag force is lower. Now, the one that makes more sense to us is the sphere. But if you understand the cylinder, the sphere, it's very similar. You have the Stokes flow. You have a kind of a region where it's pretty flat. I know there's this great transition in here. But then don't you get this drop off? And what's the great application that every fluid mechanics teacher, when they teach it, and every textbook talks about? It's a little ball about this big around, typically white, typically hit out in the field, that's nice cut manicured lawn by some person that's carrying a stick with a big wad club at the end of the stick, and they sit there and stare at the ball and they whack it with that stick and that wad on the end of this. What's that called? Golf. I've never played the game. I've heard it's very addictive if you play the game. Hence, I'm never going to play the game. Right? I don't want to get addicted to something like that. I may be finding myself having to go. I worked with a guy. He would go and shoot 9-hole or 18-hole before 8 o'clock in the morning. And then he'd go after work too. So I don't want to do that, right? But what's this? Why do they have? What's the story behind golf balls in this drop right in here? They have dimples on the golf balls, so it's not perfectly round and smooth. And this sphere is for round and smooth. If you put dimpling, guess what happens to the curve? This shifts for the same speed. It shifts so that you get a dramatic drop in the drag coefficient at a lower Reynolds number because of the dimpling. What? Yeah, smooth off the golf ball and try it yourself. They're not going to hit well on the range. They're not. The dimpling is there for a very important. It's not for mud or anything like that or dirt. It's for aerodynamics. And it shifts it over such that at a lower speed you get a lower drag coefficient. Hence the ball flies further. But then once the ball starts to slow down, the drag coefficient picks back up as if it's like a smooth sphere. And then it likes to drop. It really chews into it and drops it. And then if the person's really good, they put a back spin or they make a forward spin or a side spin. Who knows? I'm not a golf player. But there's a lot of aerodynamics in golf balls. What's the dimpling do? Helps it transition to be turbulent on the front half such that the angle of separation goes larger at a lower speed, earlier Reynolds number than if it was a smooth ball. Hence, there's less aerodynamic drag. It flies further. So here's our cylinder and cross flow. You're looking for Nusselt. What's that bar on top mean? Average. And then you have a constant Reynolds to an exponent m Prandtl to the 1/3. It's good for this range of Prandtl number, which is good. Hey, what's the Prandtl number of air? About 0.7 or a little higher. You evaluate all your properties at T sub f. What is the name of T sub f? Film temperature. And the C and the M come from a table in the textbook. Here is the C and the M. and they depend on what Reynolds number. So you have to figure out what Reynolds number range you're in. Let's say you're at 20,000. That would be right in here. You would use that C, that M, plug and chug. You'd be able to get how did this table come about? Measurements, experimental measurements, and then correlation. All right. You can read some of it. They'll give you a correlation. They'll give you another correlation for the same problem. Hey, circular cylinder and crossflow. What was this one? Circular cylinder crossflow. What? Well, different people, different times put out different papers with the same problem and different correlations. Here's another one. Guess what? Churchill and somebody else proposed a single comprehensive equation that covers the entire range. Cylinder crossflow? I got 3 options as a... You're right, you got 3 options. Which one's better? Look at this one you can use on a time-limited exam, but wouldn't you prefer to use this one with a time-limited exam? But if you're coding it up in a computer program and you don't want to do an if-then-else finding the Reynolds number, and this works for a whole range of Reynolds number, well, then use that one. So this correlation, 752, those coefficients. This correlation, 753, those coefficients. So you got to be paying attention to what equation and what table. Now, there's a pattern here. These are all evaluated at the film temperature. Here, I can just tell by this Prandtl number to the S. What do you think? That Prandtl number is evaluated at a temperature, but the temperature is the S temperature. What's that? The surface temperature of the cylinder. And then this Prandtl number would just be the Prandtl number evaluated at the T infinity. Don't do film. This is just the fluid far away temperature. So you can read in the textbook about the equation 753 and what they're describing there. Again, somebody, maybe Smith did this one and maybe Jones did that one. Different people, different times, same type of problem, but a different structure to the solution. What happens if I don't have a circular cylinder? I have a non-circular cylinder. I have a, doesn't that sound funny, a square cylinder? But that's some of the wording. What? Square cylinder. I'd rather call it maybe a square rod. But anyway, here, and you can tell the data, whether or not it's aligned this way or that way with the direction of flow. You use this for the length scale and the Reynolds number, or you use this in the length scale, the Reynolds number. Aren't they different? Well, D is D, but look, it's from tip to tip or side, middle of the side to the middle of the side. They are a different length scale. Good for this range of Reynolds number. This is your coefficient, plug and chug. Likewise, hexagon, people have done it. Look at this one. This is a pretty much a flat plate. And what do they give you? They will give you the on the front as well as the back. When you think that there's a different Nusselt number, a different convection coefficient on the front versus the back of that plate, sure. So there you go. I know I covered this up, but there's a table, just the one that we just talked about. And if in the textbook, the next line, or at least one version of the textbook, I don't know if this version has the same formatting and everything. You read the sentence and it says, again, we caution the reader. Who's that? That's you. You're the reader. Not to view, like not. Don't make a mistake here. Here's the caution. Not to view any of the foregoing correlations as sacrosanct. Yeah. So this is my next clicker question. So we reread that sentence and we says, what are they saying? What does that sentence mean? Does that sentence mean don't trust these correlations? They haven't been verified by others? Does it mean that these correlations have been verified by others and can be trusted? These correlations are very accurate. These correlations have large uncertainty. Or there is a typo in the book and sacrosanct is not a word in my vocabulary. When you're confronted with a new word, when I was your age, what did I do? I got the book off the shelf. You get the phone out of the pocket. And what do you do with the phone out of the pocket? You do a search like I did, but it's electronic search. Instead of on paper with a dictionary, you do it in electronic form. So in Google, I just say, define this word for me. How do you do it? That's the way I do it. I just say, define sacrosanct. Let me see what this means. And, oh, look at this. This is so cool. You can even get somebody to pronounce it to you. You can learn how to say the word. Who's done this? Only a few people. Isn't this pretty cool? Hey, this is 2019. I know a lot of faculty teach as if it's 1950 still. It's 2019, and there's some slick stuff out there to help us learn. And I find this is just mind-boggling. It wasn't there a couple years ago, was it? Been there for a while? Yeah, but 2010? You think so? I don't think so. Anyway, so it's like, don't view it as sacred or hallowed or involatile or, it can be upgraded. It can be changed. It can be improved over time if somebody does a better job of measurements. But basically, some of this is, it's just the nature of the beast. There's a lot of uncertainty in these. So I think that's the best answer. Don't trust the correlations. Well, they have been verified. It's just don't put a tight error bound on them. A lot of people are looking to find fault with your published work. If they can, then they can publish a big paper saying, "Ha-ha, I've done a better job than Joe Blow over here," and "Ha-ha, that's great to do in academia, right? Show up your neighbor." So there's a lot of people that have checked these correlations, and within large error bounds, they're good correlations. What about a sphere? Look at this. It's kind of a constant with the function of Reynolds number. There's some limitations. Check your Prandtl, check your Reynolds, check your mu over mu sub s to make sure it's within this range. Typically, that's easy to do. And all properties are evaluated at what temperature? The fluid free stream temperature, T infinity, except for mu sub f, which is evaluated at Ts. They're very common when you see this structure, either with Prandtl number or viscosity in the correlation. Let's solve a problem. We have a 20 millimeter diameter sphere made of steel, so it has a conductivity given, the thermal diffusivity of steel given, and the mass density of steel given. Is dropped in a large tank of water. The sphere is initially isothermal at 360 K and drops until the center temperature is 320 K and the water temperature is 280. So the sphere may be assumed to quickly reach the terminal velocity in the water. Estimate the terminal velocity in the water. So a big tank, you got filled with water. You drop the hot sphere and it starts to go. And after a while, the velocity is constant. It's called the terminal velocity. How would you get the terminal velocity? Review of fluid mechanics. Could you do it? You would do a FBD. What is that? That's what every instructor in senior design will ask you to do repeatedly. You got a drawing of something. Give me a free body diagram of that. Show me the stresses, strains, forces, torques, whatever. So we have a sphere. What are the forces acting on it? You have the weight of the sphere. You have the drag associated with fluid drag going down. How are you going to get the weight of the sphere? Isn't that the mass times g? Isn't the mass the density times the volume multiplied by g? How about the drag force on it? I'm not done with the free body diagram. I'm just saying, what is the drag force? What's the equation for that one? Well, we go back and say C sub d was equal to F divided by 1/2 rho v squared a. So this is going to be 1/2, well, put the CD first if you like. The drag coefficient, 1/2 rho v squared, which is our dynamic pressure, times some projected area of the sphere, which is related. It's the projected area of the sphere. Is that 4/3 pi r squared, or is it 4 pi r squared? Answer A or answer B? Or pi r squared? Answer C. Or 2 pi r squared? 2 pi r squared? Answer D. Okay, if I have a sphere dangling in the room over there, 10 foot, 20 foot away from me, and I look at it, and I just look at it, and the sphere is painted black, does the sphere look like this if it's sitting over there? Yeah, that's kind of like the area that I see of the sphere. All right, somebody says I have a radius r, and I want to know the area enclosed by that circle. What do you call that? That's an area of a circle, isn't it? What's the area of a circle radius r? Pi. So what's my projected area? Isn't it not B? It's not that one. Isn't it pi r squared? It's my projected area. Okay. Well, anyway, it's fluid mechanics. You're going to lose points because of fluid mechanics, not because of heat transfer. That's why you're going to lose points, aren't you? Okay. So then you have this area here. You get the drag force. What's my last force that I need to include on this free body diagram to get the terminal velocity? Buoyancy. So there's an additional force like this, and it's the force buoyancy. How do I calculate the buoyancy force? It's somebody's principle. Whose principle is used? Newton's principle. He did everything. No, not Newton. Finally, it's not Newton. Reynolds' principle. No, it's not Reynolds' principle. Got to go back a long time in history. Galileo's principle. No. Archimedes' principle, isn't it? Archimedes' principle. And so what does it say? Archimedes' principle says that the buoyancy force, F buoyancy, is the weight of the fluid displaced by my object. Well, how do I calculate the weight of the fluid displaced by my object? Get the density of the fluid, the volume of the object, and G. Look good? Archimedes' principle, the weight of the fluid displaced by my object is the buoyancy force. All those three. So let's write out our equation to calculate the velocity, the terminal velocity. So we have two ups. We have C sub D, 1/2 rho v squared plus rho of the fluid volume G equal to rho of the solid volume G. Does that look good? So my V, if you want to do it this way, is going to be rho S minus rho F, volume G divided by, what is this, 1/2 rho of the fluid, isn't it? I should put a rho of the fluid there, and then I have C sub D, and then I do the square root. This will give me the terminal velocity. The challenge is not knowing the densities. I get that. That's easy. G, the volume, I get that. Is what's the challenge in this equation that's hard to figure out?
We need the area.
Did I leave it out? Yeah, I did. This area projected area. Okay, thank you. What's hard in this equation? What is C sub D? And in your mind, you're saying C sub D is a function of RE. All right, just got to get RE. What's RE a function of? V. I'm trying to solve for V. So at this point, I think I show students, yeah, this is how you get, I'm looking for C sub D. It could be up here, 100, 200. It could be 1, 2. It could be 0.1, 0.2. I mean, it can range a lot, but I've got to find the Reynolds number. But the Reynolds number, I need to know the terminal speed at which it's falling in the fluid. So this is my illustration here. So fluid mechanics, I'm sure you've been confronted with this. Did I already tell you about this? I'm sorry if I'm repeating myself. What's this device called? A merry-go-round. Did you have fun with one when you were little? They were already outlawed, huh? I had a lot of fun. But I think the sharp metal and everything, and probably a few teeth and jaws and other bones were broke. Especially when I was little, we'd go and there'd be, I don't know, 20 kids on one of these. And the little kids and the big kids, the little kids flung off. The big kids really pushed it like way too fast. And I'm sure in my memory, I'm a little kid about 6 years old, and the big kid's only about 10 or 12 or something. But anyway, I think there's fewer of these, but I had a lot of fun. Anyway, you got to get on one of these. You ever sat there and tried to figure out how to get on? You got a bunch of other kids on it. You just got to get on. You just got to, the same game here. You just got to get in the game. So don't stand there and say, well, I can't get V. I'm trying to get V, but I need C, and then it depends on then it depends. Just pick one and go for it. Probably the easiest is pick a drag coefficient. Because once you pick a drag coefficient, you got a velocity. Once you have the velocity, you can get a Reynolds number, and you can get an updated drag coefficient. So if I went back and I looked at this correlation, what would you pick for a Reynolds number or a drag coefficient? I mean, I don't think I'm in Stokes flow. And I don't think I'm, super high Reynolds number. And I have a sphere, and I'm just going to pick right in there. Just drag it over. What's that? 0.6. And then start the game. So if you did that, you would be well on your way to solving this. You'd get a V. Once you have the terminal speed, then you could go back and forth. I forget what the final, I think I have it on the next slide. No, I have it on another slide. There. All right, I know there's a lot to digest here. I think 0.39, I think I started with a Reynolds number in this one. And then I found the speed, and then I updated the Reynolds number from 10,000 to 60,000. But the drag coefficient changed from 0.39 to 0.41. And then you update, and then the drag coefficient's 0.41. Then the drag coefficient's 0.41. The Reynolds number around 55,000, 60,000, somewhere in there. And then finally you converge, and there you go. That's how you do it. 1 or 2 iterations, you're going to be there. So that's how you get the terminal speed. Now that wasn't the only question for this problem. So we go back to our problem. And now that you have the knowledge of the terminal speed, calculate, this is wrong, calculate the initial rate of cooling. What's the initial rate of cooling? How would you calculate that? Well, you would assume that it falls and initially or very quickly reaches the terminal speed. So you know the Reynolds number, and you want to get the Nusselt number. So go get a correlation where the C Reynolds to an M, Prandtl to a power, typically a third. All right. Once I have the Nusselt number, then I get H is equal to that Nusselt number, K divided by D, because the length scale is D on that Nusselt number, just like D is on the Reynolds number. Once I have the H, then I can get that Q is equal to HA, the initial temperature of the sphere, Ti, versus T infinity, the fluid temperature far away. Okay, that's pretty easy. What is the area? Is that my projected area? Or is that the surface area of the sphere? Right? So we go back and ask the clicker, or just give the equation. Is it 4 pi r squared? Is it 4 pi r squared? Yeah, it's 4 pi r squared. Okay. So that gives me the initial rate of cooling. The next question is, what is the height that the water tank is needed to cool the sphere such that the center temperature drops from 360, the initial uniform temperature, down to 320? This is a challenging problem here. So if you want to know the the height, let's say the L. And I don't know why a lot of students have trouble with this one. It starts right up here. Your assumption is it immediately is at the terminal speed of falling in the fluid. And you want to know what is that L, right? How would I find it? Well, what is my relationship between velocity, distance traveled, over time? Isn't that my relationship? Professor, are we in dynamics again? I mean, really, come on. This is heat transfer. Why do I don't want to use this equation in heat transfer. No. The length is simply the terminal velocity times the time required to achieve that level of heat transfer out. You're going to check the BO number for this problem. The BO number is unfortunately not small. So it's not tiny. If it's not tiny, what do you cannot use? You cannot use lumped capacitance. Oh boy. You have to use the series solution. But I mentioned about the series solution, the Fourier number is almost always greater than 0.2. You're going to use only one term in the series solution. And so what you need to do is say, this is the center temperature of the sphere. It needs to get to 320. So the theta, or the T asterisk, which is at the center, sometimes 0 is a subscript for a center, is going to be that temperature at the center minus the temperature of the fluid far away divided by the initial temperature minus the fluid far away. And you're going to be looking for the correlation where the center temperature is a function of the Fourier number. Let me pause for a minute. Who knows where I'm going and can point out the equation that we need to use for this problem? Can you do that? Do you have your textbook? Professor, I was having a happy time of zoning out. I really wasn't listening anymore for the last 5 minutes. I don't know where, I wouldn't even know what class I'm in if somebody woke me up. We didn't use lumped capacitance. We used the next method. What chapter was that next method described in? 5. You're in the right chapter. You are good. Somebody's going to be looking in chapter 7. Sorry. Yeah, this problem's in chapter 7, but it's requiring you to use something out of chapter 5. Did you find it? What page are you on? In section 5.6, you have the exact solutions for infinite cylinder as well as the sphere. It is 5.53c. Is that the equation you tabbed? This approximate solution for the center, it's equal to a constant C1, the exponential of minus zeta 1 squared times the Fourier number. What? So we have to calculate our BO number, which is not tiny, and I have to go over here, I think. And the BO number is not small, so we use the series solution. And when we calculate the BO number with the radius as the length scale needed in table 5.1, you find that it's 2.11. You have to do some interpolation, and you find zeta 1 in that and it's, if the BO number is 2, then zeta 1 is 2.0288, which is the number in the table. So you can check, it's okay, it's 2.06, okay. And then you're going to need the C1. So you get these two values out of the table. 5.1. Okay. Right. So you got the C1 and the zeta 1 from the BO number. Well, I don't see, Professor, how that helps me calculate anything. Well, you calculate this one, knowing the temperature that you want. You have the C1, the zeta 1. What's the only thing you do not know in this equation? Fourier number. So you calculate the Fourier number, which is theta naught divided by C1 natural log of that times the minus 1 over zeta 1 squared. You just solve for the Fourier number. Okay. Once I have the Fourier number, how does that give me the time needed? Well, the Fourier number is defined as alpha t divided by r squared. And so the time needed to achieve that degree of cooling is a Fourier number, r squared divided by alpha. You can stick it into that equation to get the length, which is the terminal velocity times the time needed to achieve the cooling. And that's the height or the term. And so the final answer is 3.1 meter. There's a lot of work in that problem. So the Fourier number came in here. Get this out of the way. Again, I check it because we did the one-term solution. It needed to be better, greater than 0.2. That was our initial assumption, which is good. It's consistent. So it's about 1.5 seconds of fall time. And so the height or length of the tank needed is the time times the speed. And it comes in at 3.04 meters. A lot of work, isn't it? All right. I see that I'm out of time. I emphasize these sections are being skipped. And I'm going to go ahead and stop right now.